Hello. In this video, I'm going to explain problem 16 from the 2013 F equals MA contest. In this problem, we have a very large number of small particles in a spherical cloud. And initially, they are at rest, and we are given that it has uniform mass density rho naught and occupy a region of radius r naught. And then the cloud collapses due to gravitation, and the particles don't interact with each other in any other way, so it's just collapsing solely due to gravitation. And they're asking for how much time passes until the cloud collapses fully. Now, if you look at the problem, if you look at the options, you'll see that they all have different units. At least clearly some of these units don't match. And this seems to be really the only difference among all the answers, because otherwise they all have the same constant, 0.5427, which they've told you is square root of 3 pi over 32. So it seems that really the units are just the important part, and that will give you the clue that this is really a problem about dimensional analysis, or at least checking dimensional correctness, and really not about anything related to actually attempting to carry out this calculation. If you do attempt to carry out this calculation, it turns out that it is possible, but very difficult. And in fact, this idea of a spherical cloud interacting gravitationally is actually related to analysis of the behavior of the long-term behavior of the universe, which I think is pretty interesting. And you can probably see that this problem in its original form is pretty hard by the fact that it mentions International Physics Olympiad right here. So anyway, what are we going to do for dimensional correctness? Well, what we're literally going to do is check units, or to check how units combine to form the units we want. So we see three parameters in this problem. So R naught, and then we have the gravitational Newton's constant g, and then we have rho naught. Now, what are the dimensions of each of these? So these brackets denote the dimensions of a particular quantity. So the dimensions of R naught are just length, which we write as L. The dimensions of rho naught are mass over volume. Volume is length cubed, so we write mass as m. Volume is L cubed. And now, what is the gravitational constant? Well, we know that the gravitational force looks something like this. And now, what is force? That is mass times acceleration. So that's mass times length over time squared. These two each give a mass. And this gives a distance. And of course, since it's r squared, it's a distance squared. And now to make these units match, since from this we have g equals f r squared over mm. And so what we end up getting is that the dimensions of g are the force ml over t squared. Then we get L squared from the R squared, and then we get two m's in the denominator from the two masses. And thus, we get that the units of g, Newton's constant, are L cubed over mt squared. So now we can ask, what is the time? So, of course, the units of time, the time to collapse, is just going to be time, which we denote with capital T. And so, if we're going to assume that time to collapse will be some constant. Now, it turns out that they've actually told us that it's root 3 pi over 32. That's less important. Multiplied by R naught, by some power of R naught, so we'll say R naught to the alpha, times G to the beta, some new power, and then times rho naught to the gamma. So and then what we're going to do is that we're going to solve for alpha, beta, gamma with linear equations, or with a linear system of equations. And this is the sort of pretty standard method for solving problems regarding dimensional analysis. However, I will make a slight note at the end about this. So for now, let's do this. So on the right side, our units are time. On the left side, the units are time. On the right side, again, the units are, so we have R naught is L to the power alpha, and then we have G, which remember is L cubed over mt squared, and that's all to the beta, and then rho naught is m over L cubed to the gamma. And so on the left side, we have L to the power 0, m to the power 0, t to the power 1, is L to the power alpha plus 3 beta minus 3 gamma. Then we have times m to the power negative beta plus gamma, and times t to the power, notice it's t squared in the denominator, so we get negative 2 beta. And now we can just match everything. So we have this linear system, alpha plus 3 beta minus 3 gamma is 0, matching the powers of L. Then we have negative beta plus gamma is 0, matching the powers of M. And then we have negative 2 beta equals 1, matching the powers of T. Now, if this were a fully general 3-variable system, this might be a little bit annoying, but fortunately we have systems where, or we have an equation where beta is isolated, so we can go ahead and do that straight away. Beta is negative 1/2. Then we have a system where it's just beta and gamma, so we can solve that gamma is just the same as beta, and that will be negative 1/2. And now we can solve for alpha. And in fact, from these first two equations, since negative beta plus gamma is 0, and then 3 beta minus 3 gamma is just negative 3 times that amount, we would see that alpha is also 0. So even just the first two equations, regardless of the third equation, tells us that alpha is 0. And so what that tells us is that the time to collapse is basically proportional to, there's no power of R naught, but there is a power of G and rho naught both in the denominator, but with the square root. And now, before we go back and declare victory, it's good to do a sanity check and to actually use some physics, or at least some physical ideas. It's often in dimensional analysis problems, yes, it basically just becomes a linear system and you don't have to think that much about the physics, but it's still, even in those cases, it's still good to use physics as a sanity check when possible. So we should ask, do the values of alpha, beta, gamma make sense? Right? So let's just write here. Well, let's think about it. Let's start with beta and gamma. So beta equals negative 1/2 is basically saying that the time is proportional to 1 over the square root of g. Right? Now, g is just a constant, but if you think about it, let's say we lived in a universe where gravity was stronger, then it makes sense that the particles would collapse in less time. And if gravity was weaker, it would make sense that the particles would take more time to collapse. So this at least intuitively makes sense. Now, obviously, that intuition alone would not necessarily tell you what power of the gravity it is. It doesn't necessarily tell you that it's negative 1/2 specifically, but it does tell you that it at least should be negative. So that's good. Now, how about gamma is negative 1/2? That tells you that t is proportional to 1 over the square root of rho naught. And this also makes sense, that if the particles were denser, then they would, there would be a stronger gravitational force pulling the particles toward the center, meaning that it would ultimately collapse faster. Once again, that doesn't necessarily tell you that it should be the power negative 1/2, just that it should be some negative power, but at least it makes sense. And now finally, how about alpha equals 0? This is basically telling that t is independent of R naught. Now, this is one that's perhaps a little bit surprising. Now, does that make intuitive sense? Well, let's think about it. One thing that you may know, and this is perhaps a fact that is perhaps not as easily, or at least not, certainly not obvious, but if you have a uniform sphere and you are inside the sphere, then it turns out that the gravitational force is actually proportional to the distance from the center. And at least the intuitive reason, you can go through calculations more rigorously, but the intuitive reason is that basically if you are at a certain point inside, let's say here, then only the stuff inside would actually attract you, would actually have a net impact and would actually attract you toward the center. Whereas the stuff outside, it turns out that any spherical shell, if you have a uniform spherical shell and you're inside a spherical shell, it would actually exert a net force of 0. And so all the stuff outside actually would not contribute. And so actually the gravitational force will be proportional to the distance from the center, basically because your distance, or basically the gravity would fall off as 1 over r squared, but it would actually increase as r cubed because the mass inside this sphere, the sphere that actually counts, would be proportional to r cubed. And so thus the gravitational force would actually be proportional to the distance from the center. And what that means is that actually, no matter how far the particles are out in this system, for example, let's say I just added more particles out here at the same density, then these particles would just be attracted with a stronger gravitational force and would just fall into the center in the same amount of time. Because yes, for example, maybe they're twice as far away, but at every moment, they're actually going to have twice as much force. And so it'll just fall to the center in the same amount of time. And so it actually makes sense that t is independent of r naught, although that one is clearly trickier to notice or to make sense of. So anyway, it's good to, again, the moral of the story is that it's good to at least do a sanity check before you just claim victory. And sometimes, here we did linear equations because it wasn't too bad, but sometimes if you, for example, know certain well-known relationships, then you can often find the linear combination or the combination of powers of quantities that would make the right dimensions. You can often find it faster than just, than just dimensional analysis, or than just using linear equations. So like, for example, if you know that, for example, if you recall that kinetic energy is, 1/2 mv squared, then you know that if you want a unit of energy, then that needs to be, a unit of mass times a unit of velocity squared. And then sometimes you can use those relationships to, or for example, the units for pressure are actually just the units of energy divided by the units of volume. And so if you look at the units of energy, it's the unit of mass times velocity squared. But then here we have a volume, that's a capital V. And so it actually ends up being the units of density times the units of velocity squared. And so sometimes you can use those kinds of relations to figure out the appropriate linear combination faster. But in this case, we didn't need those techniques. So anyway, we know that we want both g and rho naught in the denominator and r naught to be completely absent. And there's your answer. And in fact, the fact that r naught doesn't matter, in fact, would actually eliminate every other option. So perhaps that's another way of solving this problem. All right, and I hope that was helpful. The unfortunate thing about this problem is that if you haven't learned the idea of dimensional analysis, or perhaps hadn't seen a problem, or at least been trained to think of dimensional analysis as something that's important, then chances are you may have just no clue at all how to even begin to approach this problem. Whereas, if you've heard of dimensional analysis, this becomes a fairly trivial exercise. But anyway, thanks for watching, and I hope that was helpful.